population dynamics, but in view of applications to ecological problems. So now we will have a lecture on mathematical modeling of epidemics. So, but this is not a completely different subject, because if we think about modeling epidemics at the level of the population, of the human population or animal population, then it is also a problem in population biology, in population dynamics. And we can actually use many of the ideas and concepts that we have developed for the dynamics, population dynamics applied to ecology, to study problems in epidemiology. So that's also a classical topic. If most books on mathematical biology that you open will be a section of epidemics. And so, but this today will be softer mathematically. So I hope it will not be very stressful, although we are talking about disastrous diseases. Mathematically, this is more like almost an entertainment only. Okay? So let's start just by recalling some facts about epidemics that have historical importance. So the first epidemic fully described in the history of humankind is what is called the Plague of Athens, which was an epidemic that raged in 430 before Christ. During the war of Peloponnesus. And it was described by one of the first historians, in the sense that a person that really wrote about this, which is Thucydides. And so there's some information about the disease, actually, yeah? Which were headaches and hard cough and so on, but 1/3 of the population died, including Pericles, one very important ruler of Athens. So it's called Plague of Athens, but it's used, the name plague is used in a non-technical term. It's not bubonic plague, okay? So actually we cannot know exactly what it was, because I mean there were no medical records or something like that. It's just a story told by Thucydides. But, well, there have been archaeological works trying and joining with DNA of bones that have been found, blah, 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 a lot of things. And so it seems that this would be actually a bacterium, okay? Well, that's all what you know, which, I mean, this is called Epidemic Typhus. And so that's what you know. But now, let us just remark two things. So this is an epidemic that has actually raged without anything opposing them, any public health managers, because they couldn't know what to do. And could be no, I mean, there could be no way of getting away or quarantine. All of this is, I mean, this is a very long time ago. There were no such things. So it raged in the city-state of Athens, but actually killed 1/3. Okay, let's look at it from the positive side. 2/3 were not killed. It's important. It didn't kill everybody. okay? So it's not everybody that dies. So this is the first thing. Even naturally, even without any, say, force opposing the spread of the epidemics and being highly lethal, even though it's 1/3, which is very high mortality rate, okay? But it's actually it's comparable. Yeah, I mean 1/3 is high, okay? So of the population. So not everybody got infected, and not everybody that got infected probably died. So we don't know. So, and it was probably caused by a bacterium. Okay? So that's another fact that it's also important. We'll recall this in the last part of the lecture. So, and also, well, it seems that it came from Africa, but nobody can be sure. So, then there is plague. Plague is the main disease that of the modern human history. Plague is real problem, and let's say, okay, the modern human history since the 14th century. So in the 14th century, there's the first plague in Europe. So we don't know if there had been other plague epidemics. There are no records. So, but this entered through the southern part of Italy, okay? And actually, there was a wave of epidemics spreading all around Europe. And this caused a very high mortality. And it was, I mean, it was a real big problem. And today we know that this is also a bacterium, which is called Yersinia pestis. In Yersinia, it comes from Yersin, which was a French doctor that discovered the agent of the infection. It discovered the bacterium, and the bacterium got his name, Yersinia. And so, just to frame this in time, so this was at the end of the 19th century. So it took a long time to discover things. And here, let me make just an aside. So there's something very that we, as people from the 20th and 21st century, sometimes don't have the historical, I mean, a more historical view of things. It is very recent in humankind that we know what diseases are and how they are caused. This is things have not even 200 years ago. And in the middle of the 19th century, you have the works of Pasteur and Robert Koch, which discovered that diseases could be caused by small living animals or whatever, living beings that you cannot see, but then get into your body and you get sick. Okay? So this is a very fantastic theory. So imagine the amount of science and the knowledge that you have to have in order to come to that conclusion. So what did people think before? So there were several proposals. So the oldest proposal was the idea that there's something in the air. So there were two things. People agreed that there were contagious diseases, but it was thought that contagious diseases would be typically sexually transmitted diseases, because then you have a contagion, you have a contact. Now, the contagion theory, which turned out by Pasteur and so on to be the one that is true. But before that, before you had all the knowledge that could take you to the conclusion, the contagious theory had difficulty in explaining, for instance, plague. Because I am here, I get plague, I die. The guy 1 kilometer from here dies next. So I've never seen the guy. How could there be contagion? So that was seen as a real problem. And I mean, without the knowledge of microbiology, you could not even expect that to be true, that to be any contagion. Okay? Well, what happens actually is you have first to discover that there are such things like bacteria. Okay? So you need microscopes. And where come microscopes from? Come optics, which was developed because of astronomy. There are very curious connections in the history of science. And then you need a lot of, so even if you say, okay, no, they are small, the germs are small, living beings and it cause the disease, you don't know how the disease is transmitted. So this is the end of the 19th century. There has been real progress of that. It has been discovered by a French guy, Pierre-François Simon, in the last years of the 19th century, that plague was transmitted by a chain of infections involving the rat and the lice, and the lice, not the fleas, and so on. So, this is difficult to determine, okay? So there have been field observations and so on. There's a building of enormous, but still, this allowed to take public health measures. So when Robert Koch discovers that actually the bacterium of cholera, then you don't know how it is transmitted. So it took a time until actually through the works or proposals of John Snow in England, that bacterium, the cholera was transmitted through water, stagnant water. Yeah. So it took a time to know this, and people rejected explanations, and so on and so on. So, okay, then you can take public health measures. Okay, you go, you say, okay, the problem is contaminated water, we treat water. Okay, the problem is the rats, hygiene, no rats, okay, and so on, so on. But still, you don't know how to save people's lives once they get infected. So that's a new step. How do we, knowing all of this, knowing what's happening, how it's transmitted, how can we actually find a way to avoid consequences, sometimes mortality? Okay? So this took a long time, and it is only through Fleming in the 20th century, in the end of the 20s and the beginning of the 30s of last century, that Fleming discovers penicillin, almost by accident. But it was not used, and there were no widespread use of that until the Second World War, where you had one of the problems of war for the armies is that they are in an environment where it's uncontrolled and there are lots of diseases. I mean, there's things like cholera are very important and were important. So they used penicillin and actually saved a lot of people and so on. So only in the 50s and the end of the 40s and the 50s that you get antibiotics. So it's very, very recent in the human history that we know what the diseases are, how they are infected, and so on. So I tell this story for everybody when I can, mainly as a defense of science. Right? Science is actually under attack, not only in Brazil, but in other countries also. Okay? But you see, even this connection with optics and astronomy, in principle, why are you looking for the planets? Okay, maybe the planet has nothing to do with the diseases, but well, there is the optics thing, the connection, and many developments in science of the, in this case, of the 18th, 19th century, which took us to discover something which you could not even think about without the whole building of the science. You could not expect to know that there are living beings that we cannot see. This looks something as crazy as dark matter or something like that. You can see the thing, but it's there, and you get sick because of this. So it's really a defense of science as the connection from the basic micro biology studies to real applications saving human lives. Okay, so let's get back to the lecture. So plague has been very important, and there were 3 important pandemics. Pandemics is epidemics that have a very large extent. Usually people would say the whole world, but well, it's not the whole world, it's a very large extent. So there was the called the Plague of Justinian, which spread in Constantinople. And it actually stayed at the Mediterranean, and it did not go into inland, exactly because this is Middle Ages, yes, and Middle Ages means no roads, so it couldn't spread. Okay, so but well, things changed later, and the Black Death, which is in the 14th century, entered Europe and actually killed 1/3 of the European population. And the 3rd pandemic began in China at the middle of the 19th century and killed 12 million in China and India. Okay, there's still plague in our times, and in arid region of U.S. Here's, yeah, this, and well, I didn't write it there. Where you have more mortality due to plague is in Kazakhstan, which is also a big desert. So this kind of arid region, you have rats and so on, they're still not eliminated. Okay? And so in Brazil, you have, this is the evolution of the cases of plague in Brazil. So that it got extinct, but you know, 1 or 2 years ago there was a case, yes? It's not on the plot. I don't remember, more or less 1 or 2 years. There was 1 person that died of plague in Brazil. Okay? So it's circulating. It exists. It's non-zero. Well, okay. But now, I mean, it is a bacterium, okay? And being a bacterium, you get antibiotics and you treat people. Oof, okay? You have to go, I mean, have to be quick, but it's something which is not so much an issue nowadays. And then the 3rd case of real important epidemics was called the Spanish flu, which has nothing to do with Spain. Actually, it's an error, but well, it just, I mean, the expression got viral at the time and so on. And so it's just an influenza, which is like a flu, and this was lasted more or less 1.5 years, more or less, and all regions of the world were attained, and 50 million of human beings died. So, and 1/3 of the population of the world was at that time was infected, which is very high infection rate, very high. So this little beast, this virus, is was actually very good in spreading and also in killing. So we will discuss this at the end a little bit about the virulence and mathematical models. And just to mention this, and there were São Paulo was affected as well as Rio and so on, and so the first death occurred in October 21st, but kind of one month later it was over. So again, people didn't know what to do against because it's a virus, not a bacterium, and so on. But people didn't know what to do. It's transmitted. There's no carrier. There's no vector. In technical terms, people should say that it's not a vector-borne disease. It's a directly transmitted disease, and people didn't know what to do. And but yeah, I mean, it started and it extinguishes itself naturally. So we will want to have this in our models, that at least for certain diseases, epidemics should be like something that starts but then declines. Okay? So this we have seen this in all the examples, that it's not all the population that gets affected. There's no such thing, everybody dying out. Okay. So, okay. So, how do we build models in epidemiology? So we will start with well-mixed populations. Means that all individuals can get in touch. Every individual can get in touch with every other individual, which is clearly a problem if you want to study epidemics with spatial considerations. In the city of São Paulo, I'm surely not in touch with people that live in the other side of the city. So, but anyhow, if you look for the things on a large scale, that's a good approximation for many cases. If you want to look at a small scale, you have to be more specific. And we will look for special homogeneous case, which means that we don't want to take into account space. Okay? So for public health models that address actual epidemics at the level of a city, you have to take into account sometimes space. Because, well, there are parts of the city where you maybe have the disease and other parts not. It depends. Like, you know, there are diseases associated with poverty and so on. Therefore, then in this case, you have to take this into account. But we will go and consider space as homogeneous and not important for our models. So what we will do is take the population, and let's think about the human population in this case, but it could also be animals, okay, or plants could be. But let's have in mind humans. So we divide in 3 classes. So one class of the population is the susceptibles. The other one is the one of infected. And the third one is the one of recovered. So this will be a good model for diseases that you get recovered and you get immune, for instance. Okay? It's not all diseases, but there's a class of diseases. Okay? So from the susceptibles, you get to the infected, but not naturally. You need a contact, and I will draw this like this means contact between S and I. Take people from S to I. And S goes to R naturally. So this is called a SIR model. It's just the simplest model, not the simplest, but the non-trivial simplest model in epidemics and in epidemiology. And so here we are considering that people that get infected are also infectious at the same time. So we could go for other models. And at the end, I will tell you a lot of models that you could build. But you could have incubation time. Or you could have, which is still worse, time where the person is infected, has no symptoms, but is infective, which is the hell for many diseases. That's a very dangerous situation. You are transmitting without knowing that you are transmitting. So we can think about this as a structured population, if you want to. Okay? So we don't want, however, to discuss the demographic dynamics of the population. So, as I told you, for instance, for influenza, the total population, I mean, for instance, as I told you, in Sao Paulo it took more or less 1 month. The total population in Sao Paulo didn't change at that time. And the number of people that died, I mean, still even being a serious disease, but it did not change very much the size of the population. And moreover, if you take into account diseases like the common flu, common influenza, like where you don't have death induced by the disease, you can, over the time span of diseases, usually weeks or months, you can consider the population to be constant size population. So we want to put this into our models. We want the population to be constant, which in our cases is, means that S plus I plus R is equal to N, and N is a constant. Constant population, which, you see, will be nice mathematically because we will have 3 functions, S, I, R, but there's constraint on them. You can calculate R from, say, one of them in terms of the other 2, 3 equations that actually can be transformed to a 2-dimensional system where we are already, everybody's already a PhD on planar systems and so on. Okay? And this is a good approximation for diseases that the epidemics that last a certain amount of time where the population does not change. That means that there is time scale of population change, of demographic change, and there is this time scale of the disease, and they are completely different. Okay? If this is not true, you have to take into account the other, you have to make other models which can be built and so on. Okay? So, we are also not talking, I mean, you could talk about, say we want to talk about dengue. So this, you could do this with this kind of model, but well, to have a better model, you should take into account the mosquito dynamics. So they have also the population of mosquitoes, which can be infected and susceptible and so on. So this first discussion is very, I mean, it's like for these diseases, like influenza, rubella, measles, and so on. So the first idea is that here is very important, pay attention, point, that the susceptibles change in time and the population is constant, so that we are not considering people, newborns, okay? So it can only change negatively by contact with the infected and transforming susceptibles into infecting, okay? So therefore, I will suppose I have a term which is proportional to S times I. So this is first of all, it's okay. It means that the per capita change of the susceptible is proportional to the number of infective people, which is okay in principle, okay? Could it be a more complicated function? Sure, but let's stay with the simple one, okay? So, that's back here, and it has to be a negative sign because susceptibles will disappear and reappear as infective in the next equation, and then there's some constant, okay? So, now comes the point. This constant should depend on the total population n. Why? So, let's think about common diseases, like, let's say, influenza, okay? Measles, or this kind of thing. So, consider the city of São Paulo, or the metropolitan region of São Paulo, 20 million people. There's a certain dynamics of the disease. You now go to Campinas, it's 1 million, 2 million. They have the dynamics of the disease, and it's pretty similar. You go to a small city, the dynamics are also pretty similar. Okay? So, the dynamics means the function that describes the number of susceptibles or infected at a given time should not be dependent on the size of the population. Okay? So now, this means that you would like to have a model such that the variables, the true variables, should be the proportion of susceptibles in the population, the proportion of the infected in the population, not the total number. Okay? So that if the population is larger in a city than in another, still the dynamics will be only connected to the proportion of infectives and susceptibles and recovered. So now this thing here doesn't have this. If I just write this like that and say R is constant, and I divide both sides by n, then I get this here, and say you get this here, okay? So this would be, you could call this a small s if you want. This is the fraction of susceptibles in the population as divided by the total number, minus r times s times the fraction of infective. So, what? There's an n here, okay. Sorry. So the fraction. But this depends still on the variable s, which is not a fraction, it's an absolute number. So if r is proportional to 1 over n, and say it is some beta over n, then you get, instead of r here, you get a beta here, and you get an n here, and this gives you minus beta small s, small I, which are the fractions. Okay? Nice. Now this is only what is called a frequency-dependent model. And we want to have frequency dependence. It's characteristic of the transmissibility of the disease. Beta would be higher beta, means what? That a certain number of infective create a higher number of, infect a higher number of susceptibles that will get infective. So it's kind of will be connected to how. No, in principle, what the beta, we will take it without dependency. We will take beta to constant. Now, let us discuss why we want frequency dependence. Where does it come from? Okay. So what would you expect? I mean, you can do individual-based models, stochastic models at the level of the individual and scaling this to populations and so on. Well, this can be done, but it's not our topic. But you expect to beta to be proportional to infective contacts. Yes? If you don't have infected contacts, beta should be 0 because there's no transmission. Okay? And if you have a lot of infective contacts, then beta should be high. So, now, here comes a very important difference between human societies and animal epidemics in animals or in plants. So, if I live in a city of 1 million, I have a certain number of contacts. If I live in a city of 10 millions, I don't have 10 times more of contacts because of the social structure of human society. You get in contact with your friends, with your family, with people that work with you, and the people that you cross on the street and so on, so that your actual number of infected contacts should not depend on the size of the population because we have a social structure. Okay? So this can be made there. In the first of our schools, we had a very nice lecture. I think you can find this on the website probably, by Victoria Colisa, which is a person in mathematical epidemiology, which showed us how from network of contacts to obtain the value of beta, for instance, which is very nice. Okay, so connecting network theory to transmission of diseases. Okay, so, but this is connected to our structure of the society. If you go for animals, there are social animals, but say it's not the case. There can be density effects. Okay, if you think about typically what people think about is like cows. If you have more cows, a more dense population, there are more contacts, because cows are. It's not a natural setting and so on. But it is important that in some animal epidemics, the number of contacts may depend actually on the total number of animals. Right? And this is also true for phytopathogens, for diseases in plants. Okay, if you have more plants, more packed, then there's more transmission. So there should be some density dependence. So here we will take this R to be some beta over n. Beta is constant, and we'll go now on with that. But this is a point that's not very often discussed in books of mathematical biology, and people just go over it, and it's a very important point. Okay? So let's continue to build our model. You have the first equation is this one. Then you would say the number of infective should increase in the same way as the number of susceptibles decrease, as we are not taking into account that there are no deaths in birth in this model. Then the number of affected created at a certain amount, at a certain point of time, is exactly the number of susceptible that became infected. So it's like an efficiency one case. Okay, but well, then for an infective, you need also some way that they get out of the infection, which is we will just say that there's a constant rate of infective becoming susceptible. Okay, and becoming recovered. Sure. So this is a constant rate. Let us just look what is the meaning of this constant A. This constant A, let us look at the equation for I. So let us not consider the first term, which is the term which says there's an influx of new infectious individuals due to the susceptibles that are being transformed into infective. So the term which describes the decay of the number of infected is this one, okay, minus AI. Okay? So this is like negative growth rate Malthusian equation. It's just an exponential decay. If you don't have any susceptible anymore, maybe you can stop some quarantine or something, then you expect that there's a certain decay. So this thing here, time. Let's look at the dimensions. This side, they have susceptibles over time. Susceptible, not. Today I'm making a lot of mistakes with the word. So you have infective over time. And here you have infective. Therefore, A, the dimension of A has to be time minus 1, which means that 1 over A has dimension of time. So what is this time? Okay. This time is the typical duration of the disease. Okay? So it's the time scale of the disease. So it obviously, if you want to connect this to actual medical data, you will have a lot of statistics and so on, because the disease's duration is actually not a constant, and so on, so on, so on. But it gives you the typical time scale of the disease, okay? If you're studying influenza, that's like 4 or 5 days, okay? So that's the time scale. Maybe it's 3, maybe it's 4, it's 6, it's not 1 year. Okay? So important interpretation, because we will discuss things about this. So this is our system of equations, where we can look at that. And first of, okay, so there are 3 equations, which are a system of 3 equations, which seems pretty much simple. I used simple mass action terms, like the Vodka-Tergan terms, didn't take into account many other effects that could be important. So it's the simplest case. Okay. But again, no solutions, qualitative analysis, all the whole thing again. Okay. So, okay, the first important point is, if you add up the equations, okay, if you add the first to the second and the third, then immediately you see that on the right-hand side, this one will cancel this one, and this one will cancel this one. Therefore, the time derivative of S plus I plus R is 0, okay? You agree? Just add up the equations. And this is the total number of the population, which we consider to be a constant. Okay, that means that we are okay. The model is compatible with the assumption of constant population. Okay, if it were not, you would be in trouble. Okay, so this is the first thing. So what is the actual? So usually, in the previous lectures, right, you would like to have the solutions or the qualitative behavior of the solutions and so on. But let's look at this by first asking one question. Do I want all the solutions and so on? So at the first moment, I want just to know if I have an initial population of susceptibles and some initial population of infective and no recovered. So this is the beginning of the epidemics. I have a certain number of susceptibles, a certain number of infective that had been introduced to the population. Usually, you would take S0 as the total population, and the initial value of I would be a very small number. Okay? But we don't have to make this approximation right now. So this is the start of a population. So we have a certain number of infected individuals introduced in a given population with S0 susceptibles, and knowing the values of R and A, which is non-trivial, non-trivial at all, okay? So known in population. A is easy because it's depending on the disease, but R is complicated thing, okay? Anyhow, but let's suppose that you know the parameters and then you know the initial values. We want to know if there will be an epidemic or not. Why? We know that certain epidemics, certain populations or certain diseases may kind of invade a population of humans, and sometimes not. Okay, so so we want to know, and how is our mathematical description of an epidemic, which is not necessarily the same as people in public health use, but actually it is it's consistent with what people use, is say, if I have a certain initial number of individuals, if the number of individuals at the further time t increases, then I have an epidemic. So I introduce a certain number, and it spreads. Okay? Then I say epidemic. Okay? So in order to know this, here's the only mathematical point of this lecture. You have the equations here, and you notice that at a certain time t equal to 0, you can take the second equation here and consider it at time equal to 0. So then you add on the right-hand side here the R, S0, I0, I0, okay? Which results in something which is I0 times this. So if the factor that is so at time 0 you have the dynamics of the infected, time equal to 0, is equal to I at time 0. So R S0 minus A. So if this derivative is positive, it means that the number of infected will be increasing, therefore epidemic. Okay? So, and when is this positive? When this guy is positive. Okay? So what you would like, if that, okay, is that if this thing is positive, which is here, it's written here, then I have an epidemic. And if it's negative, the population is initially decreasing, okay? So, therefore, S0 bigger than A over R is a condition for the existence of an epidemic. It is sufficient, and well, they can also show that it is necessary. So, on the other hand, if S is initially not initially, S due to the equations, the derivative of S is always negative. Okay? Therefore, S is always smaller than S0. S0 is the initial population of susceptibles. So it is smaller there because of this. So if S0 is smaller than A over R, which is this case, then S of T is smaller than R over A for all T. Therefore, substituted in the second equation, you get this, and that you get that if at the initial time S0 is smaller than A over R, the time derivative of the number of infected is always smaller than 0. There's no epidemic. So summing up this is there's a single inequality which gives you the conditions for the existence of an epidemic in a given population, which is this one. If the number of susceptibles is larger than A over R. So we can rewrite this in this way, okay? Just dividing by I mean, as you want to divide everything by A over R, and what you get is this, that this factor here must be bigger than 1. This is called the basic reproductive ratio. And the fact is that even in the most complex systems, more complex diseases, you usually have something like R0, which is the condition of invasibility of the disease in a given population. You have a certain population with a certain number of susceptible people, introduce a certain number of infective people, then you have a condition that gives you if the population, if the pathogen of the disease will spread or not, and this is the condition. Okay? So R0, bigger than 1, epidemics, smaller than 1, no epidemic, here in this model. Okay? So, very nice. Now, let's make sense of R0. So, first of all, look at this. There's S0, R, and A. So 1 of the A over A, as I discussed here on the blackboard, is the typical time scale of the disease. Okay? Yeah. Yes. Increases? Yeah. Yes. And then you will show you that's possible. And not in this model. In this model, the number of infective for a long time is 0. An epidemic is just, I mean, it's the initial increase. I'm not saying the epidemic is the total occupation of the population by the pathogen. So initially it increases. So you get infected guy into a susceptible population. Will it spread or not? Okay, but obviously then there's the nonlinear dynamics given by the equation, and we will show that the solutions to this model are actually decaying to 0 over time. Okay, this will be the next step. So first, just make sense of this. 1 over A is the typical length of the infection, the time span of the infection. So the longer 1 over A, so the smaller A, the longer the infection, and the longer the infection, it's more likely to spread because people are infective over a longer period of time. Therefore, this condition here seems to make sense that it's proportional to 1 over A. So it's proportional to the 1 over A, to the time span of the disease. Longer time span, more spread. And, well, the larger R0, if there are more susceptibles, then there are more chances to occur an epidemic because you have a recruitment pool of people that can get infected larger. So this is kind of should be more or less obvious. R is the measurement of the transfer tax of susceptibles to infected, so it's the transmission. And so the higher the transmission, the more infective the disease, and therefore the more infected the disease, then it's more likely to have the disease, the epidemic spreading. Therefore, the fact that this is directly proportional to R is okay. It makes sense. Okay. So, but remember that R was our beta over n. Okay. So or R0 is actually beta over n times S0 divided by A, and S0 over n is the fraction of susceptibles over A, which means that R0 does not depend on the total population and on the frequency of susceptibles in the total population. Okay? So, okay, let's look at the plots in the phase place. So first of all, S plus I plus R is equal to N. This is nice because we can forget about the last variable R. We don't care because it's calculated in terms of the two previous variables. So you don't need to bother about this, which means you can study everything on the SI plane, which makes plots nicer and easier to understand. Here you have a line of initial conditions, because at the initial conditions you have S plus I equal to N because the number of recovered is 0. So this is the line of possible initial conditions. And these are the trajectory in phase space that give you the behavior of the epidemic. And what you see here is that the trajectory, all of them leave from this initial conditions line here, and some of them increase and then decrease. And other ones decrease directly. No epidemic here, epidemic here. But they go to 0. And they go to 0, but they go to 0, and you see at here, at the large times, when the epidemic is over, well, large times, the number effective goes to 0, but the number of susceptibles is different from 0, which means not everybody got infected, which is compatible with our, say, natural history of epidemics that we kind of discussed in the beginning. So this is okay. So this incorporates the idea that naturally, without any public health measures, without any treatment, even though this kind of epidemic, if this is a good model, a sound model for the disease you are trying to describe, it implies that you get first the condition for the existence of epidemic, which is the inequality, R0 bigger than 1, and it also implies that the total number of susceptible at the end is different from 0, therefore not everybody got infected. Okay? So this thing I will skip and I will put it on the website. It's a little bit more mathematical and I will run out of time if I go for this. You can actually calculate, okay, the final size of the epidemic. Okay? So you do some calculations and you can calculate the total number of recovered at time going to infinity. The total number of recovered at time going to infinity means that if they were recovered, they were infective. So this is the total number of people that got the disease and then recovered. So we don't have mortality induced by the disease and so on. Okay? So you can actually calculate this. It gives you a transcendental equation and so on. But, so, okay, let's see the glories of the SIR model. It's simple. It's relatively realistic even. Here you have data. This is obviously data from a boarding school in UK. So it's a closed system, okay, which you don't have usually, okay? But, well, in this kind of experimental setup for the spread of flu, you have actually these experimental points. And you have the number of susceptibles and infective. So these are the solutions of the equations. the plot. You see for the number of infective, it increases and then decreases. And the number of susceptible always decreases. Okay. The recovered is immune. Okay, okay. I didn't. Maybe I have not stressed this point. So recovered in this case means immune. Okay. Okay. So it's not always true, but for things like flu, one season, it is true. Or measles is true. So this solution, these curves have been obtained numerically because, well, that cannot be solved analytically anyhow. Okay, so, and our R0 actually makes sense. And this is very nice because of what? So, if we believe in our R0, being this thing here or this thing here, if you want, and as I told you that this concept of R0, so just for the mathematicians and physicists. So what is the concept of R0 mathematically? You have initial state, a certain number of infective, a certain number of susceptibles. You introduce one infective guy. If the state without infection is stable, then R0 will be smaller than 1. If it's unstable to perturbation in the sense that you introduce an infected guy, then the zero disease state is unstable, and therefore it has to grow because the number of infective cannot decrease, cannot be negative. So it's unstable. So it's an stability analysis from the point of view of dynamical systems. And the R0 will be the R0 smaller than 1 will be the condition of stability of a population which is susceptible, and if introduced by one infective person or agent, this will not spread, and you will get back to the disease-free equilibrium. So the inequality for R0 is the condition for the stability of the disease-free system. Okay? So, very good. Now, so clearly this concept can be adapted to more complicated models with infectious but not infective, with models with mortality. You can adapt this rather easily, okay? And the idea will be, I want to know if the disease-free state is stable or not. If it's not stable, you have an epidemic. That's mathematically sounds very simple. Actually, with some linear algebra tools and so on, you can get, even for large system of equations, the R0 can be calculated almost in a very mechanical way. I mean, it's just doing the calculation. So, if somebody is interested in that, I can give the reference after the class, which is called it's called what? The method of next generation matrix method. Okay. So, but just with what you have now, we can have some public health, we're going to have at least some guesses about public health policies that may avoid epidemics. Avoid epidemics in this setting is just maintaining R0 below 1. Okay? So, how can I try to manage this? Okay? So, how could I, so managing this, let's say S0 is 1, so the whole population is susceptible, only to make things simpler. Okay, but how could I try to modify artificially the values of, well, of beta, of A, well, and eventually also of S0. So can you have some ideas of how can I, manage this as a public health official, how could I manage these parameters? Ideas? I didn't understand. Vaccination. So vaccination, well, this is very simple model where there's no birth nor death. Okay, then it's a constant population actually, and so vaccination is easy to model. It's just that S0 is say 1 at the total population, which is 1 because S0, small S0, is 1 minus the vaccinated guys, the vaccinated fraud. So that you decrease R0. Vaccination is very effective way of lowering our R0. Okay? So this explains situations that where you have populations that have higher vaccination coverage. And we saw like things like that, but this is not well established. We are actually working this in December about measles in Brazil and the epidemic of 2018 in the Amazonian region. It's very curious because there are cities that had epidemics and others that hadn't, not epidemics. Okay, so we are trying to see if this is connected to vaccination coverage or not. This is a difficult point because one of the difficulties of epidemiology is data, obtaining data. So one thing that in order to know why there are some cities in Amazonas had epidemics of measles and other had not. You could think about coverage by vaccine, but you don't have the data. This is not, I mean, the data are very imprecise because the data is usually just how many vaccines have been delivered at that city, which is not very informative. And usually you get the total number and not the evolution over time. And the other things is there could be different effects, like maybe it's not the vaccination, but this particular population has a higher number of recovered people that had sometime back in time had measles before the almost elimination, like me, I had measles, and so there is immunity. So, okay, so but this is vaccination. Vaccination is more difficult to model. When you have, for instance, the population is constant, but they have the number of births equal to the number of deaths. So this would be the next model. I will just show you the model in a moment. Okay, but then you have to say, okay, do I vaccinate everybody at birth, or do I take a certain moment of time and vaccinate everybody that has a certain age, or everybody of all ages? So the different strategies, which can be modeled differently by this in mathematical terms and can give you results, and you can have some predictability about what you expect from different strategies. Okay? So other ways of lowering R0. Increasing A means diminishing the time of the infections. If this is, so treat people. Okay, so treat people is nice, okay? For instance, if an antibiotic, that's perfect. Virus is more difficult, okay? But actually, you could think of treating people as just isolating them also, okay? I take them out of the population, kind of, okay? So the guy got the disease, he was 3 days infective, but the other 3 days, he was not effectively infective, he was in I don't know, in his house or something and was not transmitting. So this is a way also to think about the time of the infection, of the effect time that you have to take into account. Okay. Yeah, yeah. Campaigns for public service in general, so that you decrease the transmissibility. So this is difficult to model in this kind of model. But for instance, if you model the most simple model for cholera epidemics, you have the infected, the susceptible infected, the recovered, and the amount of cholera, free cholera in water. The transmission, of course, yeah. Yeah, I mean, everything that reduces beta would be nice, okay? So one way is so you have to know how the thing is transmitted. So we clearly know that there are diseases that are affected by the socio-economical conditions of the populations and others that are not. So influenza is not. I mean, people get influenza, get flu everywhere in the world. And even if I mean, I don't know, in the US or Scandinavia, people have flu there, yeah? And the conditions are very good. So because it's directly transmitted. It's directly transmitted and it's easy to it has sufficiently high transmissibility, and so that's it, okay? Well, so other things sometimes have either vectors, like dengue, malaria. So they have vectors. You can try to control the vectors. And this sometimes has to do with the socio-economical situation of the population, which has access to the means to control things. And this is highly dependent on how rich you are. I mean, in crude words, it's, you know, if you can live in a house where everything is clean, you close your windows and so on, no mosquitoes, okay, you don't get the malaria and so on. But if not, you're exposed, okay? Same thing is for cholera. Cholera is curious, because that's a very curious thing. Cholera was a problem in Brazil. So I know, and maybe in the next month we will have here a seminar on that. But this main modeler and specialist on cholera in Brazil, okay? A person from Fiocruz in Rio de Janeiro, Claudia Codesso. And so I was talking to her, and so she has a model, and actually me and some collaborators, we worked on developments on this model for cholera and using the model to model control of the epidemics. So we met her at a conference, and I said, Claudia, so on and so on. And you're still working with cholera? No, I'm working at Fiocruz. So Fiocruz is not like an university. You do whatever you want. Fiocruz, you have missions, okay? Because the government says, okay, we have an important disease. So you don't go to Fiocruz and say, I will study a disease that only exists, I don't know, in the Arctic. That's not valid, okay? So I said, no, cholera, there's no cholera anymore. Okay, oh, nice, good news. And what happened? Why is there no cholera? What are the public health measures that nobody knows? It just appeared. So what it is? Urbanization and public sanitation probably have cut the ways to transmit cholera, which is diminishing beta, okay? So now, let us go for some further models to illustrate this thing. So you could take into account the demographics, so vital dynamics. Vital dynamics means I have a constant population, but people die and people are given birth. So I put here on this on the right-hand side, a mortality term, which is the is equal for, okay, so this is mu times S, mu times I, mu times R. 1 over mu, okay, would be the time span of the populations, of the life of people, okay? So, and I'm considered that the mortality is constant across compartments. It's the same for S, for I, for R. I'm not modeling the disease, the effect of disease on mortality. There's just a natural mortality in the population, right? But I want the population to be still constant. So, because you know, population grow at which rate? I mean, close to 0 usually. 1% is already a lot. So, unless you are studying things over time spans of many, many years, you still want the population to be constant, but you know that actually it's constant, but they are not the same people. There are newborns and there are people that died. So then you have to put a newborn here. And you put exactly the same number of newborns as the number of people that died. So the number of newborns would be, it should compensate all the deaths. So ds dt should be something proportional to the number, I mean exactly the number of people that died, which is mu times S plus I plus R, okay? And this is N, okay? And well, these equations are written for the S, I, and R here are not are the fractions of population of susceptibles and infected and recovered. I should have written this differently anyhow. So then N is equal to 1, okay, in this case, because if you measure all the population with respect to the total population divided by the total population is 1. So you get just this term here, and this is a population which has the vital dynamics, but still the constant population. And what will happen is that you will get an endemic state. So very different dynamics. Population will oscillate, okay? So you can do this calculation. You can calculate R0, okay? So again, I don't want to go to the mathematical details. It's very easy. You can read it on the website, okay? Just for the details. But believe me, it's not difficult. But if R0 it's bigger than 1, what happens in the epidemics is that you have an oscillation. And the oscillation is damped. It decreases amplitude and goes to a constant value, which is not 0. This means the disease becomes endemic. Okay? So endemic disease. So this explains, but that diseases that are always present in the population. You have the epidemic. So every small oscillation of this would be a wave of recurrent epidemics, until they settle to an endemic state. Now, this is a mathematical thing, and in practice you have 1, 2, 3, and then it's endemic, okay? So it's not that many cycles, okay? But the idea is that you have oscillations with decrease in amplitude, and so there are damped oscillations which go to a constant value, which is called an endemic state. The endemic state, you can show that if R0 is bigger than 1, the endemic state is stable, and the disease-free state is unstable. If R0 is smaller than 1, the disease-free state is stable, the endemic state is unstable. Okay, this kind of thing is called sometimes exchange of stability. You have one fixed point, which is the disease-free fixed point, and as a function of R0, if R0 crosses the critical value 1, the disease-free state gets unstable, and you get a new stable state called the endemic state. Okay? So this is what happens if you take vital dynamics into account, and then you can go and just, I mean, liberate your imagination now. So you can, you have models like maybe you would have only partial immunity. maybe you get immune for only a certain amount of time, and then you get back to be infective, susceptible. So this would be something like that. It still has the same structure here, but there's a new connection here, which takes R back to S. This is called an SIRS model. And it can be built with the same procedures I have done here. You just have to add a term on the last equation for the recovered people, which go out of the compartment of recovered and get back to the susceptibles. That's it. This also gives you some oscillations. Also dampened oscillations going to the endemic state. Okay? So why do you have oscillations in systems? Because you have an epidemic and it goes like a normal epidemic. It increases and decreases. But then even when you have vital dynamics, or if you have this connection here, recovered being susceptible, you are replenishing the class of susceptibles. And once you have more susceptibles, you will be effectively starting a new epidemic, because the R0 is proportional to the number of susceptibles. So that's the recurrent epidemics and oscillatory behavior comes from the fact that there's some mechanism which makes S increase, either by vital dynamics, they are newborns that are susceptible, or because recovered people lose their immunity, the immunity wanes out, and you get a larger number of susceptibles. And obviously you can go for things like more compartments, like susceptibles, exposed, infected, and recovered, for instance. Now this guy, and then you have this infected and susceptible together make a new exposed. So this guy is not infectious, but he has been infected, but he is not transmitting. Right? Okay, so this can be easily done. And you can also have a different kind of things like asymptomatic here. And so you could have something very bad, if you take this as an asymptomatic, a guy that doesn't have the symptoms for some time, but is already infectious, which would give you a connection here. S and I creating either new asymptomatics or infective. So complicated, diagram, okay? So, which should be the the case which would be really bad, okay? And finally, you could, let me just in 5 minutes discuss, you could introduce mortality due to the disease. So in the simplest SIR model, okay? If mortality is not so high as to really change considerably the total number of the population, you had this equation for the recovered. They were just some proportion of people that were infective, and there was a rate of infectious that people that ceased to be infectious and became recovered. Now maybe some of them die. So I put a term, a death term. Let's put delta, if you want, times R. So there's a certain proportion of people that will die of the disease. That's called virulence. Okay? So, as you can easily see, that, not so easily, but you can calculate R0, and what will happen is that, let me write R0 here. R0 will be like this R times S0 divided by A plus delta. That's the result for R0 if you have mortality induced by the disease, if you have a virulent disease. Okay. Yeah. Good. Yeah. Actually, well, I'm making improvisation. It would be better to consider this at an infected population. Well, you can have both cases. I mean, the recovered that gets out of the infective state but dies later. That's a possibility. Or just the infective guy that dies. So that you would have di dt is minus a times plus RSI minus delta I. Okay, that's it. Yeah, and actually then it's easier to see this result from here. Yeah, because you have I times A plus delta. Then you have the A plus delta. Thank you for that. It's clearer in this way. So let us now discuss something. So, I didn't hear. It paralyzed the host, you mean? Yeah, this would affect reproduction rates. Yeah, I mean, this is... Yeah. Yeah, but in this case, you have to have some demographic behavior also. I mean, if you have to they have the population, so that you have to go to models. This is it's the kind of thing you use in agriculture for how it's called sterile male things. So you have a pest and you put some other mosquitoes or something which are sterilized. Well, okay. So anyhow, but then you have the population dynamics plus the epidemic dynamics coupled. It's also nice problems to study. Okay. So, but let me just take here the opportunity to look at this equation, and what it is saying that if the effect of virulence is, so the larger delta, more people are dying. So large delta, very virulent. Small delta, less virulence. So what you see here is very curious, that virulence decreases R0. Because effectively, it's people that are infective, not being effective anymore because they died. Okay? Well, it's tragic, but it's true. So, louder. So I'm not understanding. So you have a bacterium. You have a kind of sleeping state. Yeah, I mean, yeah. You can model this. So I mean, like anthrax, but so you have spores that and so on. Usually you go for more complicated models for these cases. Actually, you think infected and dormant and affected, not dormant, and then usually you do this more complete models. So what I want to stress is that virulence decreases are 0. And now we can look a little bit at the natural history of diseases again, because what are the most widespread diseases that we have? Tell me. Flu, influenza, okay? So influenza has very low virulence, and therefore it increases, or at least does not decrease, R0. Now tell me an example of a very virulent disease. Ebola. Does it spread? No, doesn't spread. Get restricted. I mean, there you have epidemics of Ebola, but it's always restricted. It's not, there's not pandemics, okay? Virulence is very high, which helps R0 to be smaller, okay? But, well, why are not, so you could ask yourself, why are not, from the evolutionary point of view, you'd say, okay, if you are a virus, okay, you're a disease, okay, what would you like? You would like to be transmissible a lot, but not virulent, okay? Transmit easily in a lot, and not kill my host, because then I get killed too. So, why isn't it that everything is like that? If you see, it looks like an evolutionary advantage to be transmissible and non-violent. But there are violent things. There are things that are not so transmissible. So why is it that this reasoning is not working well? It's not in agreement with what we know about the world. Yes? No, so the disease would be, it would be advantage to infect very quickly other hosts, okay, very quickly, okay, so that it can spread easily, okay. So and be non-virulent because you are not killing the host, and so you have long time exposed people, infected people, and so on. So why is it that this is that virulence doesn't go to 0 for all diseases, and transmissibility is also not necessarily very large? There can be competition, but let me come to a point that I mean, you didn't say the word, but that there is also dynamics. Yeah, before I conclude. Okay. Okay. There's also, from the point of view now, the disease, there's also a within host dynamics, okay, in the host. So, if I want to be very transmissive, I want to get spread, so I have to populate very quickly my host and make him infective, okay? But this also increases the mortality of the host. Therefore, these are not independent parameters, the transmissibility and the virulence. There's a trade-off. If I'm very transmissive, then I'm likely also to be virulent. And if I take a long time for transmission, maybe I'm not so virulent. This is not true for everything. The first example that comes to mind is HIV, okay? But in many cases, this is a crude explanation that virulence comes from a trade-off it comes, I mean, the value of the virulence and the value of the transmissibility comes from within host dynamics, and there's a trade-off between virulence and transmissibility, which is a hypothesis. You can look on it, hypothesis, virulence, transmissibility, blah, 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 and you get easily reviews on that, the status of research at this point of time, and so on and so on. So this is an interesting way of looking at virulence from the very simplest models that you build in epidemics. So you can have still many more models, like introduce the way of transmission explicitly, which are called the vector-borne disease. You have a vector, could be mosquitoes, fleas. I mean, lots of things can be vectors. You can do this, and you can put into the game the population of mosquitoes. Say you are doing dengue or malaria. You have the population of mosquitoes. You have a number of infective and a number of susceptible mosquitoes, and you have all these population. You get a diagram, more complex, and so on. So this is nice to understand a lot of things, but it has a problem. Because it's very difficult to measure the size of the population of mosquitoes, right? So while for humans, this is usually trivial. You know the size of the population, and you can have the number of people that have the disease. But for the mosquitoes, you can have a model which will be more realistic, but has problem with data. Because how can I fit a model where the parameters, the variables connected to the mosquito population are unknown and undetectable? You cannot know how many Aedes aegypti we have here. No idea. You don't have this. You don't have the population dynamic. You don't have demographics of mosquitoes. So you can do better models, but take care with connection to data. So epidemiological data are a mess. They are many times they are protected by law. Okay, so we discovered something very. I like so much this story. It was really very good that Tatiana discovered. Actually, so she's our hero for that. So Tatiana is working with leishmaniasis, and so when she came to work with me, I want to work with leishmaniasis. I told her, yeah, okay, but we need data. Otherwise, this will be just a mathematical fantasy. Okay, so you need data. So I can be a supervisor, but you need to find the data. I don't know how to find the data. So it turned out that, making short a longer story, that you can get the data by just filing a request to the law of transparency, at the transparency portal of the government. You know, law of access to information in Brazil. There is such thing. And this thing is actually older. It's 2011. Okay, but it was like that. Every public sector in Brazil has to have open data. But how do you access this? So until 2017, you kind of had to go to the ministry or the governmental body and send a letter or whatever. A complicated thing they would. So and now there has been a regulation, I think, in 2000, at the beginning of 2016, and that at least high-level governmental bodies, federal government bodies, have to have a transparency portal, and there's a internet site which gives you all the links, and then you can file requests. So due to this discovery, Now we have all the data, not only by leishmaniasis, but we have files with all cases of dengue since the last 20 years and all cases of malaria, which are really, really very nice data. So this is the situation, but we live in paradise at this moment because we have this data, but this is not the usual case for other countries. You cannot file this as easily as that. And epidemiological data are really, really a mess to obtain and to work with. Because, this depends on notifications. Okay? So if the disease is if it's mandatory to the notification is mandatory, that is easier. That it would be malaria, dengue, it has to be notified. Okay? Tuberculosis also, and so on. Okay. This is done, but with a lot of errors, because there has to be a person doing the work. People, I know, take vacations, and nobody substitute them. Ridiculous things like that. You look, you have a certain dynamics, and then during 2 weeks, no cases. Probably it's just somebody didn't put the data there. The guy got himself sick, I don't know. and nobody, this is important in small cities and maybe not in São Paulo. Okay. So that you have this kind of real problem and so on. And then you have the cases of study of epidemics for diseases that are not notifiable. How do you study the epidemics of influenza, of flu? Give me an idea. How do you study this? How do you get the data for flu? English born in school, yeah. Everybody been born in school, maybe. So, an idea, how would you, give me an imagination, people, okay. I didn't hear you. Infect the rats in the laboratory, yeah, you will get the natural history of the virus in rats, not in humans. And this is different. This is characterizing the disease, not the epidemics. You could have interviews, yeah, but this depends on cooperation of people. Cooperation, not even, I will tell you a last story about cooperation before we finish this. Okay. So, more ideas. How do you get data about flu? Okay, track the medicaments, track the drugs. Could be. Of what? Flight and traffic, but you want to study, say, only in one city, not at the regional or national level. You want to look, for instance, in São Paulo. So we want to track the number of infected people in São Paulo. There could be traffic, yeah. I mean, okay. So, Exactly. This is good. It's not notifiable, but severe cases need you to stay at the hospital, internation. You stay at the hospital, and this is something you can track. So you can use this as a proxy of the total number. Obviously, this is not a good sampling of the population, because people that have severe symptoms, as are usually very small kids or people, elderly people, then you have to know the demographics of the city. But this is things that you can get, and you can do the statistics more or less correctly by using the data about people that have been in the hospital for some days. In practice, this is only done by public hospitals. The private hospitals, which are actually very important in Brazil, in São Paulo at least, do not necessarily cooperate. Okay, but yes, this is the way. It's the actual way, because I mean I'm talking. I've been working with this kind of thing, and I know the guy it's at Fiocruz that is the person that does modeling of influenza in Brazil. It's the top guy of that, and they use this And then they use something called Sentinel Hospitals. There are some public hospitals where every disease has to be notified. They keep track of everything, also flu. Okay? But okay, again, there's no real incentive for the hospital to do this, even being public, even there's a law or a decree or something like that, an executive order. And so some of them just, I mean, there's an overflow of people that day, so they just don't fill in the forms. So you have something which in statistics is a partially observed process. You have only partial observation. You have to reconstruct the number of infected people. Actually will get probabilities for infected people, reconstructing this from data, from very fragmentary data, and so on and so on. So these are the difficulties with data in epidemics. So different from ecology. Yeah? In principle, you would say, okay, I know the number of susceptibles, the total population, and so on. I get this. Yeah, I mean, it's not like in ecology where you don't have any idea of the number. Here you have, but there's a problem of getting actual access to this data. Okay, so that's it. I had some other story, but I forgot what was what I was going to tell you. So maybe I'll tell you at another point. So okay, so thank you and good work on your projects. We are on day 4, and you have until day 6. So you better have some equations, people, okay? And try to analyze, get results, otherwise you're getting late. But today you have activity at 6 o'clock. And it has a very mysterious name, bestiarium. Now, what is a bestiarium? Well, it's a name. Historically, bestiarium is a collection of beasts only, which in the late Middle Ages and the beginning of modern era were very common. People were just making designs, drawing collection of beasts. So, but our beasts will be mathematical biological beasts. Okay, the idea is you can ask anything, but anything you want. Okay, there's no restriction whatsoever on the topic. You can pose questions, whatever you want, of any kind. But there's something which is very nice. It is anonymous. So you just write your equation on one of those, or any piece of paper. You write your equation here, and you will leave it in a box. There will be boxes around, and you'll just, during the afternoon, leave it in the box, your question. I hope that everybody pose questions. I would expect this. Make an effort to make questions, okay? So anything, and it can be anonymous, unless you want to sign, obviously. But you could, yeah, I mean, sometimes people sign, but it is anonymous. So if you are shy, maybe, and you don't want to raise a question because you think probably everybody already knows the answer, I'm the only one that doesn't know the answer, you have no problems. It's anonymous. You just put your piece of paper with the question, and it's okay. Will be taken into account at 6 o'clock this evening. And obviously, you can answer any question, but doesn't mean that you will get answers to all the questions. Okay. So thank you, and okay, that's it. Okay, now remembered what the joke I was going to tell you, but it's too late.